Hopital's rule is a really great way of attacking limits, which is sort of an earlier topic in calculus, but we come back now knowing how to take derivatives. So there are three assumptions we need. First off, assume that f and g, that's going to be the numerator and denominator functions, are differentiable. Only works if you can take derivatives on an open interval containing a. The whole punchline is going to be about what happens as x gets really close to a of the fraction f of x over g of x. Okay, we also have to assume that the numerator and the denominator at a are 0. F of a equals g of a equals 0. So remember, that's called the indeterminate form 0 over 0. Okay, and finally, we need to assume that g prime of x, the derivative of the denominator, is not equal to 0, except possibly at a. Then this limit is actually equal to another limit, interestingly enough, f prime of x over g prime of x. This is not some sort of a quotient rule. This is saying that this limit is equal to just the derivative of the numerator over the derivative of the denominator. Okay, if the limit at the right exists. And that even works if we're just approaching a from the right or the left, which is not surprising. This is from the right and the left that it works. Okay, so remember, we had these limit approaches. So you can use substitution, you can use algebraic cancellation, rationalization, the squeeze theorem. The trig limits were actually special cases of the squeeze theorem. And now we have the sixth approach called Hopital's. Okay, so let's have a look at how it works. The limit as x goes to 2 of sine of pi x, sine of 2 pi is 0, over 4 minus x squared. 4 minus 4 is 0. So this is an indeterminate form, 0 over 0. Certainly both of those are differentiable. Life is good. I usually put an L apostrophe H over there to indicate to myself and anybody that's reading my work I'm using Hopital's rule. So this is equal to the derivative of sine of pi x. So that's using the chain rule. The derivative of sine is cosine pi x, times the derivative of the inside piece, which is pi. What about the denominator? Well, the denominator says, let's see, derivative of 4 is 0 minus 2x. Okay, so this is equal to that if this exists. Now, I'm going to go ahead and see if I can't use substitution, right? This is my plan A, go to. Now, the goal is to be able to substitute. If x was equal to 2, cosine of 2 pi is negative 1 times pi over negative 2 times 2. So this is negatives cancel, pi fourths. By the way, you might compare this problem to example 2 in your text to notice how similar problems work similarly with a subtle difference if you want to take the time. I've got 3 other problems here just because I think it's important to practice some problems. Okay, the limit as x goes to 0 of x to the third, certainly that's 0, over sine x, that's 0, minus x squared, that's 0, right? So Hopital's rule applies, but right, the derivative of both of these exist. So the limit, oops, getting hasty to draw my fraction bar. The limit as x goes to 0, the limit doesn't change. Derivative of the numerator, derivative of the denominator, cosine x minus 2x. Now don't get overly antsy. You might say, oh, there's an x there. Well, but you've got to check, is this an indeterminate form? The numerator is 0, but the denominator, again, I'm using substitution. Cosine of 0 is 1 minus 0, so that is just 0. Okay, let's have a look at this one. Well, what happens here is every so often you get a problem. You just love Hopital's rule so much that you get sucked into using it, but hold on a second. Notice that cosine of 0 is 1. This is 4 minus 0. So the answer is 1/4, and you don't use Hopital's rule. Those problems are going to be sprinkled throughout just enough so that you don't jump into using Hopital's rule without checking this very important hypothesis. Okay, maybe I ought to have made problems where it wasn't differentiable as well. Okay, one last problem, and this is to illustrate. This one really is a legitimate problem. Okay, so we got 1 minus 1 over 0, so that's indeterminate, 0 over 0. LH, maybe to follow my own medicine, I should have put LH there, tells me that I'm using Hopital's rule. Derivative of the numerator is 0 minus negative sign, so that's now positive sine x, in the denominator 2x. Oh wait, this is actually an indeterminate form. This is 0 over 0. You can use Hopital's again. It turns out sometimes you get these chaining Hopital's problems, okay? This is the limit as x goes, right? Both pieces are differentiable. Both pieces go to 0. The derivative of the denominator is not 0. And so we get cosine x over 2. And in fact, 1/2, it turns out, if you did a little table and got really close to 0 here, it turns out the outputs get really close to 1/2.